Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, well, welcome back. So we're going to talk a little bit more about distributed file systems this morning. Just to summarize what we talked about last time, talked about some very basic distributed file systems, but they have these significant limitations. And so to start to get a principled handle on that, we needed to talk about what does it mean for these systems to get it right. And so I talked about a range of memory models, and kind of two things to remember from that. The first is that there are these three dimensions: coherence, ordering of events at one location; consistency, ordering of events at multiple locations; and freshness, just like ordering of events versus real time. And from that, we could see that there's this progression of weaker and stronger semantics, but that there also was this trade-off that if we want very strong semantics, then we probably have to accept that our system is going to be unavailable some of the time. On the other hand, if we're willing to accept weaker semantics, we can build a system that's always available. And there's this point that divides what's possible from what's impossible. We know that causal is the strongest semantics that we can provide while still being always available and also convergent in a strong sense. Okay, so that's kind of where we're at. And so as we design distributed file systems, one of the key questions is, do we want to play over here or do we want to play over here? And we'll do both today. So what we'll talk about today, and there were great questions last time about how do you actually implement these semantics. And so we'll talk about how to implement these two classes of consistency. I'll look at a system like the Andrew file system, AFS. I'll take some liberties and simplify some things, but to build strong consistency. And I'll look at systems like Coda that implement something that more like causal, but they give you the higher availability. And as we look at these two systems, again, the theme that will drive all that is this set of trade-offs of consistency versus availability versus fault tolerance. Finally, I want to spend a little bit of time talking about another class of file systems, cluster file systems. These are vitally important today as more of the data moves into the cloud. And so I'll talk briefly about a pretty common architecture that's exemplified by the Google file system in Bigtable, but you'll see it in a bunch of other systems as well today. And the themes here will be scalability and fault tolerance. Just to prepare you, I think this is a longer discussion than this, and so we'll either go a little bit past halfway before a break, or if it seems like we're going to have to go a lot of halfway, we'll take a break somewhere in here. So don't be worried if it feels like we're spending lots of time up here, because this is a shorter discussion. Okay, so the first implementation set of file systems that we'll implement and talk about are systems that try to provide strong consistency guarantees. So these are systems, like AFS, the Andrew file system, the Sprite file system, and more recently, NFS version 4 includes some of these features. And the question is, how are we going to implement this strong consistency? So remember, the challenge was that we've got some data cached at some of the clients, but we want to update that data at a different client. So how can that work? So we somehow have to prevent the caching client from using the data once the update occurs. So when the client wants to write the data, somehow it needs to get a message to all the other clients saying, stop using your cache. And the typical strategy is to use callbacks. So the client will tell the server, here's the new data. And I'm saying right here, this could happen either when you write or when you close, more typically. Okay. And the server now, remember in NFS, the server would just write the data to disk and return, leaving this data stranded, the stale data stranded at one of the caches. instead, we need to tell that client that it shouldn't be caching anymore. And to do that, we need a new data structure at the server. So the server is now going to maintain what's called a callback list, a list of all the caches that are currently storing that data, so that when a write occurs, it can send invalidation messages down to those clients, and they can throw the data out of their cache. Once they've done that, they'll acknowledge back to the server. The server can update its local state, and finally acknowledge back to the client, saying that the write is done, and finally the write can complete. Now, the reason this works is that we're going to enforce this idea that says, well, if we want it to look like a linearizable memory or a strongly coherent memory, we sort of only want there to be one version of the data at any given time. The way we're going to do that is make sure that when an update occurs, there really is only one copy in the system. Right? And that's the one that the server has, this new version. And so before the update can complete, we need to invalidate all those other copies. Otherwise, we're going to lose the strong consistency we want. Now, if you look at this picture, there's a lot of messages going back and forth. And one possible reaction is, wow, that seems expensive. And there's two answers to that. The first is that even if it were expensive, right, sending messages around a network is cheap, right, compared to confusing humans by giving them the wrong answer. Right? So remember my parallel make example, we stopped running parallel make, slowing down my workflow because we didn't have strong consistency. So I'd much rather send those messages. But also, it actually, if you take a step back, it's not particularly expensive. Right? Remember how NFS gave you an approximation of consistency? You had the client just periodically ask the server, has this data changed, has this data changed, has this data changed? And typically the answer is no, it didn't, no, it didn't, no, it didn't. Finally, the client asks, has it changed? The server says, yes, it did, and then the client can get the new version of the data. What this means is that in polling, you still send one round-trip message between the client and server whenever the data change. But in addition to that, you send some other messages when it doesn't change. So in fact, studies that have compared the overheads find that that callback-based schemes are actually less expensive than polling-based schemes, which is a little bit counterintuitive, right? It seems like we're doing more, yet somehow it's less expensive. But the reason it's less expensive is that we're shifting the work from someone who doesn't know what's going on, this client, to someone who does know what's going on, the server. So you only actually have to do the work when you need to do the work. All right, so this all sounds great, right? We can provide strong consistency. We can do it at low cost. But there's one problem, right? And the problem is that cap theorem, right? That says when the network becomes partitioned, when nodes become disconnected, or when clients fail, and we don't know if they're just disconnected or if they failed, our invalidation can't complete. All right, so we're going to send the write to the cache, the write will go up to the server. The server is going to look at its callback list, send the invalidation message down, but the invalidation message doesn't get there. Right? And if we want strong consistency, we're stuck, right? Because we cannot update the data and allow this client to return from its write or allow the server to send the new version to other nodes until we've somehow gotten rid of this version. Otherwise, you could have someone reading the old version and someone reading the new version at the same time in arbitrary orders. So CAP says we either need to block someone or weaken consistency. And the same thing's going to happen if the node fails. We send in a message, no acknowledgement comes back, what are we going to do? So option number one, right, the sort of what we've got right now, is to block the write. And this seems like a seriously bad idea, because now you can have a system with thousands of clients, and if any one of those clients goes offline, then all the rest of the clients may have to block, may not be able to access this data. And in fact, we're in a really bad situation right now. At this moment, no one can read or write X prime, right? Because we've invalidated all the copies that we can reach, and the write hasn't yet completed, so you can't fetch the new version. Okay, so this seems like not a great trade-off. And so it seems like we're stuck, but realize that cap says something has to block, but it doesn't have to be this write. And so what we're going to do instead is we're going to block reads at this client. And we're going to do that with leases. So we're going to change our callbacks to be leases instead of just pure ownership of the data. So a lease is the intuition is right, that it's the right to access something for some period of time. And so now when the server's callback list not only includes a list of who's caching X, but also tells us how long their lease is. When does their lease expire? So when client 1 fetches the data, it gets the data, but also it gets some lease duration that says how long are you allowed to access this data in your cache. And when the lease expires, client 1 can no longer access the old version, and that's going to let client 2's write finish. So what we'll do here is, if the network is down and we try to do the write, the invalidation message won't get through, but eventually a timer goes off and the client 1 realizes that its lease has expired and it's not allowed to access this cache data anymore. A little later, the server's lease expires. The server has a timer go off, knows that the client has now gotten rid of its data, is no longer accessing that cache data, at which point it can complete the write. It can send back the acknowledgement saying, okay, your write is completed, and we're done. So we've moved to a world where C1 can no longer read its old version, but C2's write finishes, and so we've still satisfied cap. We've given up some availability, but we've moved that availability from the bulk of machines that can talk to the server to the machine that's partitioned. We're not going to let that partitioned machine access data so that the rest of the machines can. So this is a much better trade-off in these systems. So the summary of how leases are going to work is that on a read, you acquire the lease, and if you later read that data, you need to go and renew your lease. So it looks a little bit like polling, right? But with this additional tweak where we can still invalidate you if you're connected. On a write, the server is going to send invalidations. It's going to wait for everyone to either acknowledge the invalidation or we'll wait for the lease to time out. Once one of these things has happened for every client, the write can complete. Now there is a trade-off here, right? That if our lease interval is short, let's make it a 1-second lease, right? Then there's a lot of overhead because we keep having to renew the lease. We basically lose the benefit of the cache. On the other hand, if we make it a long lease, like an hour or a day, we get rid of that overhead to a large extent, but our availability suffers, right? It may be an hour for your write to complete, which is not appealing. So the solution is bulk revalidation. That the common case is that I'm alive and that I want to renew my leases. And so what we'll do is we'll add this periodic I'm alive, keep alive message between the client and the server saying, I'm still here, I'm still reachable, and as long as that's true, the leases just get renewed implicitly. And that lets us have leases that can be a few seconds long, even if you've got thousands or millions of items cached locally. Okay. So if we go back to the kind of the scope and themes that I've been coming back to over the talk, we've got these fundamental challenges, and callbacks with leases get us into a world where performance is good, availability is acceptable. We've made a trade-off that says if you're disconnected, you're in trouble. Yeah. Yeah. Okay. Here.
So for example, here is strict consistency. It's very in some cases it might be violated. For example, let's assume that C2 is writing to cache and the C1 is also writing to cache. And the difference between two events is less than the speed of a light.
Right.
So even C1 get a message from server, invalidation message, and C1 tries to read the cache. So in that case, this could not be possible.
Right. So the question is, what if, as I understand it, is what if C1 and C2 are simultaneously writing, right? What happens in that case? And what happens is that both of them will be writing and blocking until the write completes. And one of them, so they both send their messages to the server, and one of those messages arrives first. At that point, the server sends the invalidation messages out, but the invalidation messages tag with the version that's being invalidated. Right? So C1 in this case receives a message saying X has just been invalidated. Version X with no primes on it has been invalidated. And it can just send an acknowledgement back saying, sure, I don't have X anymore. Right? And we can treat that as done. And at that point, the write can complete. In the meantime, there's this queued invalidation sitting up at from C1. And so C1, the server will now invalidate anyone that's got an old version. So it'll invalidate this version, allow this write to complete, and acknowledge. If C1 is both... Right, so what happens is that the write... Right. So the key is, so the question is, what if we have reads and writes that are overlapping in time? So we've got C1 and C2. This will be time going this way. Okay. And at this point, C1 is going to write. But in the meantime, and this write is going to begin, it's going to take some time, but we've got an overlapping read that completes before the invalidations have gone through. Right? Well, the key thing here, right, is that until the invalidations have gone through, the write won't complete. And so we're guaranteed that by the time the acknowledgments come back from the server, at that moment we're guaranteed there are no other copies in the system. And so what this means is that we're allowed under linearizability to order, to have the event happen anywhere in this range. So we can pick a moment in time and say that's the instant that this read occurred. And we can pick a moment in time and say that's the instant that this write occurred. And so we still have an ordering that everyone observes it to be consistent with real time. How do you implement this? Yeah, so the key thing in implementing it is that this write is not allowed to return until all the invalidations have made it to the server. So the server knows that there's no other copies in the system. As long as we wait past that moment, then there's an instant where there's no other copies in the system, and at that instant we can say that's when the write occurred. Okay, make sense? There's also just one other subtle point here. The server can't start serving the new version, right, until, is it worth showing here? I won't try to get back to the animation, but the server is not allowed to start serving the new version until all the invalidations come back. So even though you've sent the server the new version, it's written it to disk, if there's a read request while you're still waiting for the other reads to come, the other cache copies to be invalidated, you have to block that read request and queue it up. But your question is a good one, and just to jump forward a little bit, it's really hard to get the implementations of these protocols right. And one thing that I've found useful to do is to use some sort of model checking. And you find really devious corner cases when you model check these. They're tricky. Okay, so there's one thing I haven't yet talked about, and that is fault tolerance. So recall that one of the things that NFS did to get good fault tolerance was to be stateless. The server had no state in memory other than the current sort of data in the files. And so if the server crashed and recovered, that was fine. The client just kept retrying and everything worked. We've now added some state to the server. And so we have a challenge here. So how do we deal with fault tolerance? Well, I've talked about what happens if the client or the network fails. Eventually the leases expire. At that point, everyone else can continue. What happens when the server fails, though? when a server crashes, we lose that callback state. And so how are we going to continue operation? So we've lost our data. What can we do to get that callback state? Well, when the server recovers, it can poll all the clients and say, I've just crashed, right? And I don't know who has what. The clients can send back a list of what's currently in their cache and allow the server to rebuild its callback lists. If we have leases, we can actually even be a little bit simpler. And that is just wait for the longest possible lease to expire. And once that happens, it's safe to continue operation. And so once the alarm goes off, we know that no one's caching X anymore, and we can continue processing requests. Now, there's a nice little optimization here. All of the clients know what they were caching, and they can still have that data, just don't use it until they get a lease on it. And so in the background now, they can go and refresh their leases. And as long as the data haven't changed, they can just tell the server, basically you ask the server, I would like to cache this version. And as long as that's still the current version, the server will say, okay, here's your new lease. And that way you don't have to throw away everything in the caches. You can just, over time, revalidate it. All right, so callbacks are pretty nice, right? They enforce strong consistency. Linearizability is possible. In practice, we do variations of that, right? Open-close consistency, so we'll pretend that all the reads happen when you opened the file and all the writes happen when you closed the file. But basically, the intuition is right. We can be available, reasonably available and fault tolerant because of leases. Right, that the bad clients don't prevent progress by everyone else. It's efficient, cheaper than polling because you only send messages when needed, and it's has been widely used in research systems quite a while ago, AFS and Sprite, and then NFS version 4, a contemporary system that uses these ideas. But there still is one problem, right, and that is those disconnected clients, right? Everyone else is happy, but those poor disconnected clients are unhappy. Now, if you're on a campus network, maybe that's okay, right? That I'm probably not getting any work done if I'm disconnected from the network anyhow. And if I'm disconnected, I can call someone up and they'll fix it for me. But there are cases where that's not going to be an acceptable answer. Laptop, tablets, smartphones are fairly frequently disconnected, and I still want to be able to do my work. Also, if we go to things like geographically distributed servers, right, that we don't want to take down an entire cluster because it can't talk to the other clusters. We'd like it to be able to continue to do work locally until that connection comes back. And so in these circumstances, we want improved availability, and that just tells us that we must inevitably weaken consistency. We know that Causal is the strongest option we've got if we want to be always available. So, all right, how are we going to do that? And that was a question a couple days ago as well. How are we going to implement Causal? And so I'll talk about two ways to implement Causal that are superficially different. At the core, they're doing the same thing, but it's easier to talk about them slightly separately, and I'll try to bring them together at the end. So Coda and a number of other systems do implement something like, again, client-server Causal, again, kind of playing games with the open-close semantics instead of individual reads and writes. But here's the idea. The first thing we want to be able to do is make sure that I can read things when I'm offline. And so prefetch everything I think I might need when I'm connected. So in Coda, they call this hoarding. You go hoard all the data that you want, but it's just prefetching onto your local disk. All right, so both of our clients have done that. And then let me just add a little detail here that'll become, see why we want this in a minute, that we can think of every snapshot of the server's state as having a logical time. Okay, so let me call the current state version 0, v0. And we'll just make note of the fact that my current prefetch data is version 0 of the server's state at each of the nodes. So now the network can go away, and clients can be walking around. I can be in a coffee shop that doesn't have a network, or I can be on the beach, and I can be reading and writing my data. And so here I've got client 1 reading X and writing Y and Z. I've got client 2 writing X and reading Y and Z, and that's fine. Now, when we reconnect, we need to replay the update log when we reconnect to the server. So this is really very closely related to the idea of a replay log for transactions. I log my updates as they occur while I'm disconnected, and when I reconnect, I can replay those updates at the server. So here, client 1 reconnects to the server. It sends its updates, and it tells the server that it applied those updates against version 0 of the data. The server says, great, it updates its local copy of the data, and it's going to keep track of, for each of the objects, that X is still version 0, but Y and Z are now were written at version 1. Or it took us to version 1. These are the versions that are valid as of version 1. The server can then reply back to the client saying, okay, you are now at version 1 of my data. Okay, so now when C2 reattaches, it can say, I applied a write to X against version 0. The server can see that it updated the same version of X, and so now we were at version 1, we've made some changes, we're now at version 2, so we'll call this new version of X version 2. We'll reply to the client, and notice that some things have happened since version 0, and so in order to keep the client state current, we need to fetch updates, and so we kind of cycle through this, get them back so they can read things again. And so the server replies saying, okay, if you will apply these updates to X and Y to your state, you will be at version 2. So what we've got here is the set of logically concurrent writes, right? That we sent X, Y, and Z to both places. There were reads and writes that were logically concurrent. The first client sent its updates back, the second client sent its updates back, and we brought us up to the new version of the state. But remember the problem with Causal. Right? You could have multiple nodes updating the same object when they're disconnected. And so here we are in the state we just left. Client 1 is still at version 1. The server and client 2 are at version 2. And what happens now if client 1 updates X? Recall that these writes are conflicting because they conflict if both update the same object, but neither happens logically before the other. And so we're now at X prime, and when we send the data back, the client says, I updated X from version 1. But the server knows that X is already at version 2, which means there was a miss. That's how the server can detect that there was a concurrent update. In particular, what the client is saying it believes happened is that version 1 became X prime. And what client 2 is saying, I've got my update, there's a little bug in the slide, is that it believes that, well, no, before version 1 became X prime, version something became X double prime, and that there's a concurrency here. And so we can detect these conflicting writes, and what we want to do is keep track of both of them. Right? So again, we'll now say that X double prime was the right thing in version 2, but at version 3, we have both X double prime that was version 2 and X prime that were version 3, those were concurrent updates. The client can send, the server sends back to the client, we're at X double prime. If you would apply X double prime to your state, you'll be at version 3. Yeah. Right, so we've weakened consistency. We're just going to provide causal now, not sequential or linearizable. We're doing that because clients are disconnected. So the clients don't have a connection to the server, but they still want to be able to locally read and write their data. Right, so we had to give up some consistency in that case. Okay. Oops. Yeah. In what kind of systems? Absolutely. I mean, that's what we're doing, right? Well, sorry. So the point here is that, so the question was, version control systems, handle this case, and that's right. We have 2 logical concurrent updates, and the consistency layer can say these 2 updates were logically concurrent. Some layer above that may understand the semantics of those updates. And by understanding those semantics, it can then maybe merge those updates. But the consistency layer shouldn't do that. It doesn't know what's inside of the updates. It just knows that they happen concurrently. The layer above that, in this case the version control system, could say, oh, these are updates that I know how to merge. But there are other cases where you just can't, sometimes version control systems have to give up, saying, I don't know how to merge these. Sometimes there are rules like, doesn't really map to causal, but banks have this rule typically that all the credits must be applied before the debits to an account, and so they would play with things that way. So there's different rules that apply in different circumstances above the layer of consistency. Okay. So that's what I was about to say, right? That a read of X at this node now is going to return both values. And some layer above that might pick or generate some single result. Maybe it adds them together, maybe it picks the bigger one, maybe it merges them in some other way. On the other hand, if we now do a write, the write is going to supersede both of these updates. Right? In particular, when the client goes back to the server and says that I wrote X triple prime at version 3, the server can observe that that happened after all the writes to X that it knew about. Therefore, it happened logically after them. It can throw away the old versions, and now we just have version 4. So that's how we can, as concurrent writes create multiple copies of data, we can, over time, collapse those down when a new write supersedes them. Yeah?
What kind of conflict resolution do file systems use?
Right, so Coda said that it's a file system. It understands directories. So in the case of directories, if 2 different updates to a same directory affect different entries in the directory, it can merge them. For regular files, it doesn't know. And most systems, so Coda, Microsoft NTFS had a disconnected mode, and Dropbox, someone did the experiment a few days ago, that if you do concurrent updates, it will keep both versions. And so what most of these systems do is it'll keep both versions, and now you as a user need to look at both versions and see how to merge them.
It will create 2 copies of your file.
Yeah, that's the most common thing I've seen for file systems. Yeah, I don't know that Dropbox is causal. We just know we know that it's not sequential. We don't know that it's causal. I suspect it's not, but I don't know. I don't know what protocol they're running. But any system that's, I know that any system that's causal or weaker. I don't know that, but every system I know of, right, that works in these worlds, if you're going to allow disconnected writes to occur, then you can have concurrent updates. And the typical thing to do at a file system level is to just keep both versions because we don't understand the semantics. Now you can add hooks to the file system saying, for this type of file, here's how to merge things. But
is this done at data block level or at data item level? The way you are saying.
At blocks or files, yeah. For Causal, you would almost invariably do entire files because of the semantics. You could implement it at a block by block level, but I think in Causal you do it file by file. When you do stronger semantics like linearizability, then block by block makes more sense, or is a reasonable choice. Either is a reasonable choice in that world.
So in case of HDFS, since computation moves to data, so do you think this will be necessary?
So we'll talk a little bit about HDFS. At the HDFS layer, to a first approximation, the way to think of HDFS is an append-only write-once file system. You never have multiple writes to the same file. So they don't really have the same type of consistency problem. They do, I'll talk about the specifics of GFS, and HDFS is similar, but they do have some very weird consistency semantics that they implement. But they argue that it's not too bad because of the simple ways that it gets used. There's often a layer above HDFS, HBase, for example, that does provide linearizability of updates. So above that, they do enforce this stronger semantic. Okay, so that's what I wanted to say about the client-server implementation. That you can ship, basically cache things locally or prefetch things locally, ship the updates to the server. And by keeping track of the version of the snapshot that you're looking at and of the data that you're updating, we can keep things causal. The basic idea here is that we need to make sure that what the version number at a client says is, I need you to order my updates after this version of the data, and because that's the stuff that I read. Then I did some updates. So as long as my updates come after that version, everything will be fine. Sometimes, though, you want to go beyond client server. An example would be going across multiple data centers, replicating data across multiple data centers, or allowing clients to synchronize peer-to-peer. All right, so for example, if I'm on a plane, I might want my laptop to be able to synchronize with my tablet. So I don't want to have to go back through the server because I'm disconnected. Some systems actually have noticed that there's some music systems that are normally client-server, but to save bandwidth, if you've got two different clients in the same house, they'll actually stream from one to the other if they've already got it cached on one. So there are cases where you want to use this kind of richer topology rather than always going client-server. So can you provide causal in this case? And it turns out you can. The reason that you can, fundamentally, is that causal is going to work for disconnected operation. And so it doesn't require serializing everything through a central server. We're partition resilient, and so we don't want to require there to be a single server that we always go through to communicate, because we want to be resilient to partitions. So the challenge here from going to client server to multi-server is that there's no single point of ordering. In the client server case, the server kind of could look at these epochs of time, and you read this version and then you did some updates. We know where your updates are ordered relative to my version of the data. But we can no longer summarize the state of the entire system with this single version number. And so what we're going to do instead is have each server maintain a logical time, its logical time, and a version vector. And the logical time is when it generates a local event, here's the time that we're going to give to this local event. And the version vector is an array of logical times that tells me what this client's perception of the other node's current state is. So what events have I seen from other nodes? In particular, if I look at a server's version vector, that means that S has received all writes from node I. So from I up to, so entry I in a given server's version vector means that this server has seen every update by node I up until the time, the logical time stored in that version vector. Right, so it's an array of logical times, tells me what updates I've seen from each server, what prefix of updates have I seen from each server. So now if we want causal, whenever I receive an update from another node, I'm going to set my local time to be the max of my current local time and the received logical time plus 1. Right, what does that mean? It means that when I issue a new write and attach my logical time to it, that new write's time will be after every write that I've observed. Right, so this gives me this ordering. If I receive things from other nodes, I make sure that my new logical time is bigger than any logical time that I've received. This means that any update that I create that depends on these things that I might now read will have a logical time bigger than anything I've received, which means that if the nodes exchange those writes in logical time order, then I can only receive a write after all of its predecessors. All right, so let me go through an example of how this works. So here's a simple log exchange. I've got node A and node B. I've got my version vector. I'll have a 3-entry version vector. I'll bring in node C in a minute. So initially, time is 0. Each node maintains a log and a checkpoint, the current versions of data that it's going to read. All right, so now we can have our node issue a write. And each write is going to have an object ID, a body, and what I'll focus on, and I'll pull out for each write is its accept stamp, the logical time that the write occurred. So the way to read this is that this green update happened at logical time 1 at node A. That node A's logical time was 1 when this write was generated by node A. The next write, logical time 2 at node A. Right? And we've advanced A's version vector to 2. We can now exchange logs, and in particular I can send my updates to a peer in accept stamp order. So my peer is first going to receive update 1 a day, update 2 a day. It's going to advance its logical time version vector to 2 because it now has received 2 updates from A. And if it were now to issue a new write, that new write is going to have an accept stamp larger than any entry in its version vector. In this case, we'll make it 3, logical time 3 at B. As long as these logs are always kept in accept stamp order and exchanged in accept stamp order, this is going to be fine because this write might have depended on those things, but it will always be after those things in these sorted logs. Okay. So I've updated B's version vector. So its current version vector, it's seen everything up to 2 from A, everything up to 3 from B, but it hasn't seen anything from C yet. All right, so let's add C in here. And suppose that concurrent to what we've just been doing, C has issued some writes. It's issued, write at logical time 1, logical time 3, and logical time 5. We know that this is concurrent because none of those writes depended on anything at A or B. Similarly, none of the writes at B depended on anything at C. If B were now to send its updates to C, right, it's going to send them in accept stamp order, and node C needs to do a merge sort on the incoming events versus the events it already knows about. because it needs to keep its log in accept stamp order. So in this case, we've got our accept stamp. All right, so in this case, we'll merge them together, and we now have this new order of events that's still guaranteed to be consistent with causal ordering. Now in this world, we know that 1 happened before 2 happened before 3. Now we also happen to, just chose to put this concurrent event here. We didn't have to, but it'd still be legally causal. It'd still be causally illegal if we moved it here or here. But our algorithm, to keep things simple, is just going to sort things by accept stamp order. And so this set of updates, does honor the causal relationships in our system. Now suppose that, so now some questions, right? Suppose we're in this state and C now is going to send updates to node A. Suppose they become connected and they decide to exchange updates. What updates should C send to A? Yeah, so they can compare their version vectors, and that'll identify what needs to be sent. Right? So think about, let's say that C is about to send to A. A can send its version vector down, and that's a nice summary of its state. What it would be telling C is A knows about everything up to 2 at A, 0 at B, and 0 at C. Well, now C can iterate through its log and say that, okay, in sorted order, do I need to send this? No. Do I need to send this? Yes, because 1 at C is bigger than 0 at C. Do I need to send this? No, because 2 at A is no bigger than 2 at A. Do I need to send this? 3 at B? Yes, because 3 at B is bigger than 0 at B. Same thing for this, same thing for this. All right. If we turn things around and C asks A if there's anything that it would like to tell them about, C would send its version vector up. We would see that A doesn't have any element in the version vector that dominates C, so A has nothing new to tell C. So that lets us, by exchanging these updates, by exchanging version vectors, nodes can easily and efficiently tell what updates actually need to get transferred. Let me ask the second question. We know that we're in a disconnected operation system. We've got causal, so there can be write-write conflicts. How can we detect write-write conflicts in this system? And the hint is we're going to probably need some additional metadata. So how would you detect that an update is, that we've got 2 conflicting writes? You can do it by attaching a version vector to each write. So one option is that if instead of attaching just an accept stamp to each write, if I attach the entire version vector to a write, this is the global logical time when this write occurred, then if 2 writes have incomparable version vectors, then yes, then you know they're a conflict. What if I don't want to attach an entire version vector? Can I still do it? I'm not sure. That might work. I'd have to think about it, but it's going to only, what you described as a very special case. So even if it works in that special case, let's see if we can come up with something with more general. So a conflicting write, just a hint here, is the conflicting write is going to happen when, let's go over here again. So here's some version of the data. And suppose that I read this version and produced a new version, and then read this version and produced a new version. Right? I get a progression like this. No conflicts here. But what if instead I've got conflicting writes? There's an eraser. And we started off with version X, and in parallel, we produced X and X prime. What can we add to an update record that would let us detect conflicting writes? The number of updates to the same object? Yes, I think that's right. That if each object had yes, that would work, right? If each object had a version number, then if this were version number I, and this were I plus 1, and this were I plus 1, right, then if we saw two updates that both claim to be the I plus first version of this data, then we know they were concurrent, we know that they were conflicting. So yeah, so that's good. I was the variation that I was thinking of, but it's logically equivalent to this, is to keep with each update the previous version number, or the previous accept stamp. And so you would say, I would say that if this was accept stamp 3 at A, then this update, 7 at B replaced 3 at A. And this update, 19 at C replaced 3 at A. And if I ever detect two updates that claim to have replaced the same version, the same update, then I know that those were conflicting. But it's logically equivalent to what you described. It's good. All right, last question. How do we garbage collect the log? When is it okay? We don't want the logs to grow without bound. When is it okay to throw away a prefix of the log? Pardon? Yeah, so you can look at the version vectors. And one simple way to do this is for nodes to pass around not just my version vector, but the version vectors that I know about other nodes. And then once we know that there's a prefix of writes, a minimum version. So if every node keeps track of the minimum version vector, if every node keeps track of the last known version vector of each of the other nodes, whatever the minimum number there is, they can throw it away. Now there's a problem with that. The problem there is that a disconnected node can hold everyone hostage to garbage collection. And it turns out that's a really tricky problem. In systems like, if we're looking at like and really you have two choices. One is to just say, yeah, we're not going to be live for garbage collection if nodes are disconnected forever. And that's a reasonable thing to do if you're looking at like a multi-data center replication system. Data centers shouldn't go away permanently, and so maybe it's okay to delay garbage collection if one is disconnected because you know it's going to come back. If you don't want to make that assumption, then you need to add some additional mechanism. One thing that gets done is in Bayou is that they allow, they have a commit protocol where a designated replica is allowed to assign one more commit order number to these events. That has the strange property of, although it maintains causal, the ordering actually can get shifted over time. And so it has some downsides as well, but it does allow you to garbage collect things when a node is disconnected. All right, so just to summarize implementing causal. The key idea in causal, right, is that we have to make sure that writes propagate in causal order, which means that if I see a write, I must also have seen anything on which that write may have depended. The way we're going to implement that is we'll have some way of indicating for each write what writes must precede it. One way to do that is to attach a version vector each write. Another way to do that is to have these accept stamps for each write and just make sure that the accept stamp obeys this property of always exceeding the version vector of the local state. In the client-server case, this is pretty simple to do. The server can serialize things. We can summarize the server state with an epoch number, and you just know that, well, the updates that I've created in this epoch must come after this epoch number at the server, and that lets us order everything. In the multi-server case, if we've got arbitrary topology, there's no single serialization point. So we can summarize the state with a version vector, and then by making the accept stamp for each write, for each update, exceed every version, the writer's current version vector, the maximum entry in the current version vector, then we know that these accept stamp updates will always, accept stamp order will always be compatible with causal order. One last thing to say about causal, a little bonus point on causal. So causal is highly available and convergent despite omission failures. So it's fault tolerant, omission failures, highly available, convergent, it's got these good properties. But what about Byzantine failures? What if some of the nodes can corrupt their logs? What if you don't trust some of the nodes that are exchanging logs? Can you do anything there? And I'm not going to go into the details, but the answer is yes, you can. Recall that the key idea was that we can do causal if each write indicates what precedes it. Well, if we make that history information cryptographically secure, then faulty nodes will be unable to reorder or omit things from a correct node's history. Right? If each update has a sort of logical list of everything that precedes it, and that list is cryptographically sound or cryptographically protected, then a faulty node can't change what this thing depends on. Right, so in practice, that you would typically keep just a hash of all the history that I depend on. Faulty nodes, of course, have their own keys, so they can manipulate their own history. But because they've used their keys to encrypt their history, or to seal their histories, if correct nodes ever detect inconsistent histories from a faulty node, they know that that node is faulty. And there's no way for a faulty node to get you to believe two incompatible histories. So all a faulty node can do is fork its history. This means it tells one correct node ABC, it tells another correct node EFG, and those histories are incompatible, but those disconnected correct nodes can't detect it initially. But later when they talk to each other, they can detect that this node was faulty and that it created incompatible forks of its history. So up until that point, what you have is what's called fork causal. That from the point of view of any correct node, the system's history looks causal. However, if you globally look down at all the correct nodes, you may see that this node's causal history is not the same as this node's causal history. They've been forked by faulty nodes. And so what you can do in that case is join these things together by treating a faulty node that creates two incompatible histories as two virtual nodes that were creating concurrent updates. And so the same theory that lets us deal with disconnected operation and concurrency among benign failures, omission failures, also with very small changes, lets us understand what happens when faulty nodes are actually manipulating their data. We just treat that as concurrency. And so all of this mechanism we've got for dealing with concurrent updates and conflicts, we can pull over into the case where nodes are Byzantine. We talk more about that in a paper we recently published for a cloud storage system that lets us deal with the case where some of the servers in the cloud might be faulty. So this should be a good place to take a break. We've talked about, so last time we talked about sequential and linearizable and causal. Today I talked about some ways to actually implement these things. And what I'll do in the last part of the discussion is talk about some cluster file systems like GFS and Bigtable. So Any questions before we take the break? Okay, yeah.
How are the writes actually propagated to other replicas?
Okay, so in the case of the multi-server, or the... Okay, so in the multi-server case, you're allowed to... So the protocol I described works for arbitrary topologies. The topology can change over time. It can be an arbitrary topology. So of course it would work if you just statically connected nodes to each other. And they could be statically connected. You could just pick 5 random peers to attach to. You're always attached to them. And every 5 minutes, you do a version vector exchange and then a log exchange. Right? But you could also do things more opportunistically. So we could have a system that whenever it goes onto the network, it broadcasts on the local network saying, is there anyone I can talk to? And it tries to connect maybe a well-known rendezvous server to see if there's anyone else currently online and doing those connections. And so the way that they're going to do the update exchange is first make a connection to someone that's currently reachable, exchange version vectors. Once you've exchanged version vectors, you know which you can filter your log and send the other node the updates that they don't have.
In that case, let's say both the servers have version 5 of some object.
Right.
Then let's say this server writes 6.
Right.
And this also writes 6 and it also writes 7. Then how can we detect these ones?
Right. So the accept stamp has 2 parts. One is a monotonically increasing counter, this logical time, but you could have 2 different nodes that issue updates with the same counter, as you point out. And so we append to the logical time the node ID, right? And the node ID is typically considered to be the low order bits of this logical time. And that's going to let us break ties, right? So that we're just going to say in our sorted order of the log that A is less than C, and sort things that way. And that's what will let us detect that although they both did an update at version 17, this was version 17 at A, and this was version 17 at B. And so those didn't happen at the same logical time. All right, well, let's take a 5-minute break, and we'll come back and talk about some of these cluster file systems. What I want to do with this remaining a little bit less than an hour is to talk about another fun class of file systems, cluster file systems, where we're going to make some very different trade-offs because we're in a very different environment. What I'll focus on as case studies are the Google file system and Bigtable, but that's not. No offense to our hosts. I mean, if you look inside of Azure, a lot of things look pretty similar. If you look inside of HDFS and HBase, a lot of things are similar. This basic approach is being used quite widely in cluster file systems. So I first want to talk about the Google file system, and I'll do this because we're kind of shifting gears, and because these trade-offs are so driven by the assumptions they make about their environment. I want to talk about that, then describe the basic architecture and operation of the Google file system. And as we talk about that, some of the issues that you'll see as themes are how to do atomic commits in a big system like this, performance and scalability strategies, and what kind of consistency they're going to provide. And they'll make some trade-offs that are different than what we've seen so far. All right, so for the motivation here, we're kind of going to this world of warehouse scale computing is one of the taglines, where instead of having a machine room that might be as big as this room, we're building machine rooms that are the size of a warehouse. A warehouse might have 10,000 to 100,000 nodes. 100,000, as far as I know, is a bit high still today, but not out of the realm of possibility. In these warehouses, you've got highly uniform commodity parts. So you don't buy the 15,000 RPM server class drive. You buy the 7,000 RPM PC class drive. You buy PC backplanes instead of server backplanes, possibly. You try to make this thing very inexpensive, commodity parts, and often you'll use open source software or customized software. That at this scale, you can afford to build software for the purposes that you want. Right, so if I only have 10 servers, writing my own file system doesn't make much sense. If I have 100,000 of them, writing my own file system is something that I can afford to do. Another big important factor in these systems is power. One way that these systems get described is not by the number of nodes, but by their megawatts. And these types of systems have tens of megawatts of power capacity, and they're designed to be very power efficient. Often approaching half of their cost is either the power itself or the power distribution, the hardware that distributes the power. And so being very power efficient is important. This gets done in a bunch of ways. These systems are big enough that, again, if you're just doing 10 servers, you just put them in a closet down the hall. If you're buying 10,000 or 100,000 and building a building for it, you can put that building near cheap power. And so often these warehouses are, like I know several have been located near abandoned aluminum mills, because aluminum apparently takes huge amounts of electricity to generate, so they're often built by hydroelectric dams. We'll put our data center there now. They often use passive cooling today. So instead of having big chillers, you'll just pump air from outside through the system. Or you'll use lake water or river water to cool things down. And so they're able to achieve power utilization efficiencies of 1.2 or better. Everyone kind of is admitting that they do 1.2. That probably means they're doing significantly better, but they don't give us the details. Power utilization efficiency says, for the amount of power that you put into the warehouse, right at the edge of the warehouse, how much actually makes it to the servers. And in these systems, you have to put in 1.2 watts at the edge to get 1 watt at a server, which is excellent. If you 10 years ago, you'd find lots of server rooms that were 2 or 3 as their power utilization efficiency, getting less than half their power to the servers. I think this number is probably conservative for some of the state-of-the-art ones, but they don't reveal all the details. And so the bottom line on this is that by operating at this scale, the costs shift dramatically. And sort of Hamilton had some data from 2006 where if he compares his James Hamilton now at Amazon, that if you look at a sort of regular machine room with a few hundred nodes in it, and compare that to a warehouse scale system with tens of thousands of nodes, and look at resource after resource, network, CPU power, storage, there's a 3 to 5x cost advantage when you do things at scale. And that's just something that's very difficult to ignore. And so there's a lot of challenges moving things out of traditional server rooms off into a warehouse. But the economics are just very difficult to resist. And so there's a big effort in this area. So the Google file system and others have been designed to work in this environment. They're going to look at scale. So thousands of disks, 10,000 disks easily. Right? Hundreds or perhaps thousands of clients accessing this data. And a fairly diverse set of applications. Most of them are going to use append-only writes. That a given byte in a file will be written once and never overwritten, and that your writes come sequentially through the file. Now, GFS does support random overwrite, but its guarantees are very weak. It's seldom used. It's not optimized. And for the purposes of today's discussion, and I think in general, you can just imagine that GFS is strictly an append-only file system. You're never allowed to go back and overwrite something. If you think of the system that way, that'll give you the right intuition. There is this corner case, but it really doesn't come up. They expect a read-mostly workload, where data is written once and then maybe read multiple times. Most of their reads are going to be large sequential reads. That's what they're going to optimize for. They will allow random reads again, but your performance is going to be so lousy that you wouldn't do it. What they do say is that if there is an application that wants to read sort of scattered records in a file, what you typically do is first sort all those requests that you want to make, and then issued those scattered reads in sorted order. So you get a pseudo sequential read bandwidth. Bandwidth in these systems is the primary concern. A lot of what they get used for is data analysis offline. Latency for an individual request is not something that they prioritized. And then finally, in this design, failures are common. That you expect the vast majority of time that you're operating to have at least to be in some sort of degraded mode. Right? Your common case is not everything's working. Your common case is most stuff is working, but some stuff isn't. The design also focuses a lot on technology trends, is driven by these ideas. Seeks are bad. Here's a terrifying statistic. In 1990, a Seagate, probably this meant it was a 41.6 gigabyte drive. It was, it could do 37 random IOs per gigabyte of storage. Today, looked this up last night, a 3 terabyte Seagate disk, similar class, you can do 0.03 IOs per second. Right? So the time to read a disk randomly has gone up by, what, a factor of 1,000. It's not that the Seeks are getting worse. Seeks have gotten a little bit better, but the size has just exploded. So the impact of this is that you're going to just completely optimize your system around sequential access. Right? Random access is at best an afterthought. Another design choice is that disk bandwidth is probably slightly more plentiful than network bandwidth. They're close. They're in the same ballpark, but you can get today 100 to 200 megabytes per second of sequential bandwidth off of a disk. That's a gigabit, 2 gigabits per disk. If a machine has 10 disks, you can easily overwhelm your 1 gigabit network connection, and you can even fill up your 10 gigabit network connection. And so even at an individual machine, you've probably got more internal disk bandwidth than you've got network bandwidth. And if you look at the overall network, in many data centers, the switches are oversubscribed. Right? So if you have 40 1 gigabit links coming into a switch, you might only have one 10 gigabit link going to the next switch. And oversubscription rates of 10x or more are not uncommon, although there's a lot of work on the networking side to try to get that oversubscription rate lower. I don't know, our friends at Microsoft may know if any of these have been deployed yet, but if they haven't been yet, my prediction is they will be soon. But even if you've got full bisection bandwidth, your local disk bandwidth is probably higher than your network bandwidth. So the result of this is that the implication on your design is that you want to optimize for machine and rack level locality. That going to a machine across the data center is an expensive thing to do. Going to my local machine is a cheap thing to do. And so we want to expose that type of locality in the design. Yeah? Why are Seeks, sorry. Right. Right, it's not that the seek time got worse, it's that the seek time stayed about the same, but the disk got much, much bigger. So you've got many more gigabytes of data to service with that ARM that hasn't gotten any faster. Yes, right. Right. Yeah, these are, so IOPS is sort of random access. Sequential access has gotten better, so now we're at 100. Today, I think that disk advertises a 200 megabyte per second sequential access. What was it in 90? It was probably 1 or 2 megabytes per second, maybe 3 megabytes per second in 90. So we've gotten maybe 100 times better on that front. So probably, if I had to guess, the disks have gotten about 1,000 times, 100 times larger, 41 gigabytes versus 3 terabytes, so 100 times bigger. Seek hasn't improved much, but the bandwidth maybe has not quite kept up, but isn't too bad. Right, so you're saying that, sorry. Okay, so the fact that you've got a lot of disks on a given machine, each of which has a substantial fraction of a network link's bandwidth, means that you can't read full bandwidth from the disks across the network. So if you want full bandwidth from your disks, you can only do that locally. So that says optimized for machine locality. And then this oversubscription of switches says that, well, you might be able to transfer at 10 gigabits per second between machines in the same rack. But if you look at machines in different racks, you might only have 1 gigabit per second per machine. So there is some locality here that matters that you need to expose to your file system. All right, so here's the basic players in the Google file system. You've got a bunch of clients. You've got a bunch of what are called chunk servers. And these are very simple systems that can store a big chunk of data, and you can then read it. And that's about all that they know how to do. And then kind of surprisingly, just one master. And the master is where all the magic's going to be. It's where all the cleverness is. And we'll talk about why they just have one in a minute. But let's talk about each of these categories of machines. So chunk servers store large chunks of data. And the block size here, the chunk size, is 64 megabytes was the default. The reason for these very large chunks is to amortize the seek to a chunk over a large, then sequential read. Also to reduce the load on the master. That if you have to go to the master to find out where a chunk is, that's the way it's going to work, the bigger chunks mean going to the master less often. Also, these large chunks are going to reduce TCP overheads. Right? If you want to read a gigabyte of data, well, that's going to be, 15 chunks? And so you'll contact 15 servers, 15 connections, you get it. Whereas if the chunks were, 10 kilobytes, you'd be contacting, hundreds or thousands of servers. Also important is that to simplify the design and to get good performance and scalability, we're going to cache all the chunk metadata in memory. So again, big chunks means that you can do this with a reasonable amount of memory. Okay. The second thing to say about the storage servers is the chunk servers is that the default is to replicate data three-way, three copies of each block. So we're going to throw hardware at the problem of reliability and just replicate data. That way, if one copy goes away or even 2 copies go away, you can still get to your data. But the thing to really remember about chunk servers is that they're designed to be dead simple. That the interface really is, I'd like to read a chunk, given the chunk ID, or I'm writing a chunk, and here's the chunk ID. Very simple. They don't know about the distributed file system much at all. The master is where is going to coordinate all these chunk servers. So it's going to store all the metadata in the system. It's going to maintain a mapping from a file's name to a list of chunks in that file. And it's going to maintain a mapping from every chunk ID to a list of chunk servers that are currently storing that chunk. Okay. This is also where we're going to keep access control lists, and I'll talk about leases for writing chunks in a minute. So the master is going to, with this information, allow clients to read and write by directing them to the appropriate servers. And then in addition, they do sort of managing of replication and persistence. They're going to garbage collect chunks that are no longer accessible. They'll re-replicate chunks. If one chunk server fails, they'll direct the data to other chunk servers to make more replicas. This is where all the coordination in the system happens. Finally, the clients are just dead simple. There's not much to say about them. They don't have a cache. Again, we're optimizing around sequential reads of huge amounts of data, and so you wouldn't expect a cache to be effective in that case. And adding cache coherence protocols would have added complexity to the design, so they decided not to do it. One important thing about the clients is that they can be co-located with chunk servers, right? So that you can read data locally. Right? So in particular, what's going to happen is if you've got a big parallel read, you will find out which chunk servers have the data and then distribute the work to where the data is, rather than having to distribute the data to where the work is. There's my co-location. Okay, so here's how a read is going to work. I've got my client, master, and then a bunch of chunk servers. So the first thing that'll happen is, whoops. Okay, that's a write. Okay, so a read. The first thing that's happened is that the client's going to fetch mappings from the chunk server. So that's up here. The client sends a file name, and it says what offset into the file it's interested in. And it gets back a chunk ID called the chunk handle and a list of servers that are expected to be storing this chunk. The client can then send a request for a given chunk ID, chunk handle, and a range of bytes in that chunk to the server that it's been told has the data. The server can read the data off of its disks and send it back to the client. Notice that the data does not need to flow through the master. Oh, just one thing to point out here is the application that the client gets back a list of 3 typically chunk servers. It can pick the closest one, right? So to optimize the network. Writes are a little more complicated. So we have our 3 chunk servers here, the master and the client that wants to issue the write. One of the chunk servers is designated the primary. The primary holds a lease from the master. And this is the replica that's going to coordinate any writes to this chunk. So what's going to happen first is the client will go to the master and find out where this chunk is stored and who is the primary. Once the client knows that, it's going to send the data to the chunk servers. And it does this in a slightly clever way. Instead of sending the data to each chunk server, it picks one of the chunk servers, the one that's closest, and sends the data plus a list of other chunk servers there. That chunk server forwards the data to the next one. That one forwards it to the next one. And what that lets you do is, again, optimize the network. That the client only needs to send the data once, and you can pipeline that with this send and with this send. So you can actually get the data to where it needs to go a lot more quickly than sending it directly from the client. And also, you can order these in any order so that you minimize network bandwidth. You're not going across, expensive hops more often than you need to. So send it to the nearest copy. This one maybe sends it to its nearest replica, and this one sends it to the remaining replica. Yeah. That's right. Applications will try to read large sequential chunks and effectively that way be doing read ahead or prefetching, yeah. Right. Yeah, so the question was, how do we distribute the replicas? I actually don't know what the Google File Systems policy was, but HDFS has a policy of when a client tries to wants to create a new chunk, one replica will be nearby on the same machine or in the same rack. The next one will be in a different rack for availability, and the third copy will be in another machine in the same different rack. So they've spread the data across 2 different racks for availability, but not 3 racks to reduce the bandwidth. That's their default policy. Yeah. Oh, the greedy, yeah, so you can pick whatever routing, and again, I don't know what Google's routing heuristic is, but yeah, so pick a, ideally you would look at, here's the 3 servers I need to get the data to, what's the cheapest path to get it there, and you do that. They would, so for most of this, for GFS, the application is, the client is typically an application that is linked the library in. There's a GFS library, and the client would typically be a data mining program. It would typically not be a web server because they're not optimizing for latency or responsiveness.
But that client can add that functionality.
You could layer that over that. And when we look at Bigtable, you could treat Bigtable like a regular file system pretty easily and use that. Yeah.
So what's the notion for primary replica? How is it different? You can route the write to anybody, right?
Right. So we'll get to what the primary replica does in just a second. Okay. Yeah.
Won't it be a better option that master tells the client which replica to contact instead of sending it to 3 replicas? So it can then coordinate like which replica is having a big load and those kind of things.
Right. So the question was, should the master direct the client to which of the replicas? Ultimately, the write needs to go to all 3 replicas, and so you can't reduce its load.
Saying when the read is to be done.
Oh, for a read? It's a good question. The question is, on a read, instead of giving the client the choice of where to read, you might have the server tell the client to go to a particular one that might be lightly loaded. That does seem right that you could, in the general case, try to do load balancing at that level as well.
I mean, what client can do, say, because you are saying client can optimize in terms of network. Master can do it very easily.
Okay. The reason that if I were probably one of the Google designers, what I would tell you, the reason that I would hesitate to do that is that I don't want clients to be interacting with the master very often. So they're going to cache these mappings for long periods of time. And what that means is the master probably doesn't have a good idea of what the loads are. Right? It doesn't know what the current loads are on those servers because clients don't have to go to the master to do a read. Once they've got these mappings cached, they can do reads.
That's probably a very good idea because it knows how many clients are reading which file.
Well, it knows how many have cached the metrics. Well, if I wanted to do load balancing, probably the way I would do it is when I'm a client, I would put it at the chunk servers. So the client could have a list of 3 chunk servers. It could contact 2 nearby ones, ask them what's your current load, and then pick the less loaded of the 2. And I think that would be more responsive than trying to do it through the master. It'd be more scalable, and you'd have fresher information because you'd know what the load is right now.
I understand when you say the client, the designer won't be good if the client doesn't want to contact master because anyway it's contacting once only.
It contacts the master once to get the chunk, but what I didn't show is often, or what's allowed is actually the client can provide a list of chunks to the master and get back a list of locations. And so it may just contact it once at the beginning of an hour-long job in some cases. But yeah, so I don't think you can count on the master having a good estimate of the loads.
I think Dynamo does something like designated copy or something.
Okay.
Tells you a better idea.
Right. So I think again, if I wanted to add load balancing here, I would do it once the client has a list. The client could then probe the chunk server, ask them their current load, and then make a choice based on that. It turns out it's very important in load balancing to have current information, and I think that would be pretty good. So a question was in back. Yeah.
So
Right. so the lack of not worrying about latency is another reason, but they would still, if you're trying to maximize the aggregate bandwidth, you would want to avoid hotspots. So I think there could be value in load balancing here. That could be a nice little summer project. Someone could go to HDFS and add some load balancing, but I would do it by probing, having the client probe the chunk servers, and I think that could work pretty well. Yeah. Yeah. Right. 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 So the comment there is that, and GFS does this as well, when you're doing a big parallel data analysis job, you might start by asking the server for a list of, for every chunk in this file, where are the chunks stored. Then you could assign different chunks to different worker threads on different nodes. And so again, it's useful to have information about all the copies, so you can make that assignment. Yeah. Yeah. Right, so the client, there's no, the client's cache of where the mappings are is a hint. It does time out. The client, so the client polls, and polls, I believe the client polls periodically to make sure the mappings haven't gotten too stale. At least there's reference to stale mappings. The expectation is that if a chunk server fails, if a chunk server loses its disk, you can go try to read the data there, and it'll say, I don't have the data. You can use one of the other copies. So if the data moves, you'll try to contact the old version. You'll find out it's not current, and you can go get the map. Then you can renew your mappings. The case that does cause problems, and we'll get to this, is if a chunk server becomes disconnected and misses some of the updates, the client could continue to read from the stale copy. They're going to say this is acceptable because they really only care about append-only workloads. And so what will happen is the client will hit end of file prematurely, and what you should do in that case is check the other copies to see if it's ended there too, which is not a very satisfying answer, but that's what they do. Yeah. You're right. Yeah. That's right. Thank you. Yeah. So we're finding out who's the primary, and then who has the data. Thanks. Okay. So. So we sent the data to all the chunk servers. And then at step 4, now we finally see what the, sorry, I said master again, it's primary, issued the write to the primary. All right. So we've just staged the data. And at this point, the data has not been assigned to any chunk. What we now do is have the client send to the primary a message that has a hash of the data and a write command that says, take the data that you've already received with this hash and apply it to this chunk. So you've got the small write message that comes from the primary, and it gets bound to that large chunk write that occurred. And so the primary gets the actual write message, and the primary, again, I keep saying master, the primary orders the other replicas to do the write. They say, once they've done the write, they come back, and the primary can now signal back to the client that the write completes. So the purpose of the primary is to serialize the writes to a given chunk. Even though the data propagates in arbitrary order, that data has no meaning, it has no semantic effect until the primary issues the actual write command. And there are sequence numbers in these write commands so that every replica applies writes in the same sequence. So in step 3, the data propagates, and then once it's at the last replica in the chain, that last replica signals back to the client saying the data is now staged. Go ahead and do the write. Right, so it uses a pipeline rather than a multicast or a broadcast, because that actually gives you better performance here for two reasons. One is that, well, because you're pipelining, client can be sending to here at a gigabit per second. Here it can be sending to here at a gigabit per second. Here it can be sending to here at a gigabit per second. So we're really sending this large chunk at a gigabit per second to all replicas. On the other hand, if the client sent to each one individually, you'd be splitting that gigabit per second across three connections. Yeah.
On what basis is the primary replica selected? Can't you select the closest one to the primary?
So the primary is expected to be the primary for long periods of time. So once the master, on the first write to a chunk, the master will pick one of the nodes as a primary, and then that primary will, I think I'll talk about in a second, holds a lease to being the primary. And it just continues to be the primary. You don't switch the primary in every write, mainly because the whole purpose of the primary is to serialize writes from different clients. And so you don't want it hopping around. The case that they're worrying about is, the very stressful case is when you've got 100 clients all appending to the same file at the same time. And you want those appends to get ordered in a sensible way. Okay, so that's the basic protocol. What about fault tolerance? So on a write, if a secondary fails or becomes disconnected, the write will complete at the primary and the remaining secondaries. And the client's going to get back an error message saying this write completed here, but it may not have completed here. Typically, the client will retry, but of course, we can't be guaranteed. Maybe the client crashes. And so there is a state we're in where the data made it to some replicas, but not to others. Eventually, this will get detected and fixed, that there's a version number in each chunk. The disconnected client will have the wrong chunk version number. That will prevent it from accepting any more writes until it's caught up. But more typically, what will happen is the master will eventually detect when the chunk server reports back to the master saying, here's what I've got. It will tell the node that you've got the wrong version, and it will re-replicate the right version somewhere else, removing the stale replica. But of course, there is this problem, right, that clients are allowed to read from any copy. I guess I'm going to get to that in the next slide. So this is not going to be a great answer. You also have so if the primary fails, the master is going to pick a new primary after the lease time's out. You'll start serializing things again, and again using the version numbers to make sure that things don't get too confused. If a client fails after sending the chunks but before issuing the write command, there'll be these orphan chunks that have no identity. Eventually they'll get garbage collected. Okay. But that answer shouldn't be completely satisfying because we have this read from any protocol. And so an in-progress write may or may not be seen. So you could have two different clients read at the same time, or even the same client read from two different chunk servers and see a write disappear when it went to the other chunk server. Now, you don't expect that. That's not a common access pattern. But an in-progress write is in this flux state where it's at some replicas and not others. A disconnected replica may not have recent writes, and you can continue to read from that replica for some period of time. Their argument is that that's acceptable because you get, if you have an append-only workload, this manifests as a premature end of file, and you should respond to end of file by retrying with the other replicas just to make sure you got to the end. But it's not a great answer. The other case to worry about is you actually can have a master failure with concurrent writes. And what can happen is the master becomes disconnected after writing to something at a particular offset. Another master gets elected. It issues a write to the same offset, and you can actually have two different writes to the same offset in the file. Primary, yeah, sorry. Primary failure. So you get different writes to the same offset in the file, and again, they punt it up to the application. The typical solution is to have the client on a failure retry the write. And this gives you at least once semantics, right? The client will keep retrying until it succeeds at all three, whatever, replicas may change over time, but eventually it'll get to 3 replicas and keep retrying. And then you try to make your applications duplicate insensitive. And so these records might have checksums internally, they might have sequence numbers, they might have enough metadata so that as you read these records, you can detect duplicates. So it's not, it sort of feels really painful. But one important example, just to preview what we'll be briefly talking about in a second, is that these semantics work fine for, say, a redo log. And that's going to be one of their chief, that's how it's going to be used inside of Bigtable. But, again, this is, Deline's first law of engineering. You can make it go really fast if you don't need the right answer. And they've taken advantage of that here. Okay, so I'm going to go do a little bit of dynamic reshuffling here because I do want to talk briefly about Bigtable. There's a little interlude here that I'm going to skip on master scalability. So I'll just summarize that here to say that a surprising thing in this design is that there's a single master in this allegedly scalable file system. And I can tell you it's honestly surprising for me. My dissertation prior to this work was on a cluster file system called XFS, and I was really pushing on scalability. And so we have multiple metadata servers to keep track of where stuff is located. Right? They went with just one. Right? And absolutely, I mean, it's hats off because it drastically simplifies their design. They get a big benefit from it. But it still feels like, wow, we've got to, like, you'll often hear in debates, like, well, you have a centralized bottleneck. Like, that's the trump card. Right? But centralized doesn't have to be a bottleneck. And in this case, if you actually go through the resources, people often have bad intuition on this stuff. But if you look at the actual resources being used, because they've got these large chunks and because they've restricted themselves to a particular workload, the scalability limits are there, but they're not terrifying. And so, as just one quick example of this, the master has to have metadata for every single chunk in its memory. Is that going to limit scalability? Yes, but not too badly. We have 64 bytes of metadata per 64 megabytes on disk. That means a gigabyte of DRAM can index a petabyte of disk. That means that $5 of DRAM can index $50,000 of disk. I can pay $5 if I'm buying $50,000 of disk. And you can go through the other resources similarly. You can calculate how many disks can a master support. And the key idea is that each chunk server can basically handle 1 or 2 chunks per second. That's not very many availability. So there are limits, but they're pretty large. Okay. So the summary here, it's a very simple system. And this is just, was the brilliant insight here. They drastically simplified the design. And it supports what they need to do reasonably well. But there were trade-offs. It got weak correctness guarantees, and it also isn't suited for workloads that need responsiveness or more random access. So just briefly, what if you did want a more general file system and that does allow more random access, small updates? And now you get back to something more like XFS, where you're going to have to distribute the metadata of where is stuff located and who's in charge of what. Bigtable does this as a layer over GFS. And so I'll just show you architecturally how they're going to do it, give you some intuition. I won't go into anything like the depth that I've gone into on GFS. Okay, so here's their basic architecture. And again, Azure looks similar, HBase looks similar. You've got Bigtable sitting over the top of GFS. Bigtable has a put-get key-value store interface, and they can be small records, kilobytes of records. And Bigtable is going to live over the top of GFS, where you've got a read-write interface for very large chunks of data, append-only updates, right? But it's going to use this for its log and its checkpoints. So the division of work here is you really think of GFS as a persistence layer. It's going to keep track of where big chunks of data are stored, make sure there's enough replicas of the data. If one goes away, we'll make another copy. Whereas the distributed metadata is going to happen at the big table level, where it's going to have a bunch of tablet servers, each of which tracks a range of keys. And it's going to just use GFS and write logs to it and store checkpoints in GFS. So if you look at the players, they've got one master that does even less work than the GFS master, and many, many tablet servers that are more sophisticated. And the tablet servers live on top of GFS. The master lives on top of a lock manager, which is another subsystem that I won't talk about. But it does basically, it's an agreement protocol. So asynchronous agreement happens in this lock manager. The way they're going to get linearizable efficient writes, right? So remember that in some ways this is like alchemy, right? We start off with this lead, this GFS system that gives you lousy semantics. And somehow we're going to get good semantics by building on top of lousy semantics. It seems like you shouldn't be able to do this, but they do it. So we're going to get linearizable writes on top of this. So the tablet server so here's my tablet server, and it's got three main data structures. It's got a table of recent updates in memory. It's got a log file that's stored in GFS, so it's replicated, append-only file. And it's got what are called SS table files. Each of these is sorted by key, and it's a set of key value pairs for some range of time. So these are old updates, newer updates, and still newer updates, and we'll see this in a second. So the way you do an update is you send the write to your memory table and to the log file, and then eventually, when the memory table fills up, you sort it and flush what was in the memory table out to an SS table file. And that's what I have to do on a write. The data is now safely stored. Now, how do I read the data? Well, first I'll check to see if the key is stored in the mem table. Maybe this key was updated recently. If not, I'll go to each of the SS tables in sequence and see if the read is there. And because these SS tables represent sets of writes that happened in different sequences, different flushes of the mem table, if I just try to read from each one, as soon as I hit the key that I want, I've got the most recent write, and I can return that value. Now, going to disk to each of these SS tables would be an expensive thing to do, so what they do is they maintain Bloom filters so that you can, in memory, know whether or not, with high probability, this key is stored in a given SS table. So then you only have to go to disk for the ones that actually have the data. Yeah. Yeah, so for a delete, you would store a tombstone record saying this thing has been deleted. And that would be the latest version. Now, over time, as objects are updated, as key value pairs are updated, you get these holes in the SS table, right? That this key has actually been updated is updated here, and so you would never actually read this. You never get to read this. If you go farther back in time, you get more and more keys that are no longer reachable, that are no longer stale because they're blocked by some later update. And so we have to do a garbage collection phase, and the way this works in the system is you read all the old ones and do a merge sort on them to make one bigger file. And they just do this periodically. So, instead of talking about reliability, so notice how they've designed this system so that we're going to be okay with the limited semantics of GFS. Log files are append only. SS table files, you write them once, then you read from them, randomly in some cases, and later on you read them sequentially and merge them together in sequence order to a new file. So it all comports well with what this underlying system gives you. Yeah?
During the merge, is our write blocked?
During the merge, no, you don't have to block writes because the merge is producing no new information. You can still do both reads and writes against the unmerged versions of the SS tables. And then you just need to, at some point, throw away the, it's really garbage collection, right? When do you throw away the old SS tables? Only once the new SS table is written. But up until that moment, you can use the old SS tables, and now you need the new one. Yeah? The SS tables are also in GFS. So the reads, go back to my pre-merge state. So when a new tablet server starts running, it reads the index to each SS table, right, and produces the Bloom filter for that SS table. So now it's got a very compact index of what's stored in each one. So you only have to read these parts. Later on, when it comes time to read a particular key, the in-memory data structure, the Bloom filter, will tell me it's not here, it's not here, might be here, and then I'll go read, use the index to do a binary search to find out where this key is in the file, and then go read that key. And so you expect there to be one disk operation per random read. Now you can, of course, design your application to have a good sequential access pattern. That's a great thing to do. But even if you're doing random IOs, you're kind of doing as well as you could hope. One disk seek per random IO. Well, for a random read workload, it's going to perform badly, right? This is sort of, the adversary can't make it worse than a random read workload. It's true that in a sequential read workload, if you've had lots of random writes, so a random write followed by sequential reads will not perform well. Right. Well, so you don't have to read the full chunk. You can just read a piece of the chunk. The 64 megabyte chunk is what you have to write. So this, would be something like, this might be, might be several 64 megabyte chunks. It might be 128 or even a gigabyte. But when you read, the GFS interface lets me read just some number of bytes, down to about 64 kilobytes is the minimum size. Yeah. Right, so for concurrent updates, we have a single tablet server in charge of any key range. And so both updates go to the same tablet server. Well, when they arrive, so the tablet server gets to order them, and it will append them to the log in some order. Right, so if there's no failures, it's easy, right? Because two updates to the same key go to the tablet server. The tablet server issues those writes in some order to the log file. The tricky bit, and I'm not going to get to solve it, is what happens if the tablet server fails in this process. And there are some very nasty corner cases. I think I was actually not going to tell you how to solve it. I was going to show you the corner case, and then because the paper doesn't actually tell you how to solve it either. Although the Azure paper, which has a very similar architecture, hints at it. So actually maybe just so reliability. So we could assign a new tablet server. It reads the logs in SS table. But suppose the tablet server and the GFS leader both die during an update. And that can actually happen because they might be co-located. So something you've got to worry about. And so that's your final exam. How would you solve that? So think about that. And let me just summarize. What I've talked about in these couple of discussions has been, a set of fundamental challenges that come up over and over again as we design these file systems, performance, availability, so all the IDs that you'd like from these systems. And we talked about them in the context of simple client-server systems that were very simple but gave up a lot of these properties. You can actually do quite well with consistent client-server systems in both the strong consistency case and the weaker, the causal case. and these protocols are not terribly complicated. And then what we're seeing now is a just nice bunch of big cluster file systems that make very different trade-offs, really focusing on scalability, but can still give us nice sets of properties on these fronts. All right, so should stop now. I've run out of time and gone over a few minutes. Can maybe take one or two questions, but then we should take a break. Yeah. The nodes are heterogeneous or homogeneous in the cluster? It's certainly my understanding is that like big HDFS clusters, the master often is a special machine because the one thing on scalability I didn't talk about is recovery time, and the master recovery time can be a problem. And so you really don't want the master to crash. And so they'll often have a golden machine, with extra UPS and maybe better components, server quality components so the master doesn't die. Right. Good question. So if a chunk server fails, you need to re-replicate its data.
For example, if there are two servers,
Mm-hmm.
two chunk servers, one with capacity, one with 2x. The 2x can be a replica for two different kinds of servers.
Right. So HDFS at least, and I assume GFS, handles heterogeneous amounts of disk at different chunk servers pretty naturally. It's not going to, it doesn't think of a disk as the unit of replication, it thinks of a chunk as the unit of replication. And it has no problem understanding that some disks can hold more chunks than others. The important thing on the case you talked about of recovery is that if a chunk server fails, you actually don't want to replicate all of its data to some other chunk server because that would be incredibly slow. Right? If I've got a terabyte of, a 1 terabyte disk going across a gigabit link is 8,000 seconds, right? At best, speed of light is 8,000 seconds, probably. So, several hours. If I've got 10 disks, each of 3 terabytes, you don't want to do that. So what you do instead is called declustered reconstruction in the RAID context. Randomly assign the chunks to the remaining servers with a little bit of a constraint that you don't put the same chunk on the same server. And by doing that, you're no longer having to bring all of the data to one server. Instead, each server has to get about 1/n of the data, and each server needs to supply about 1/n of the data. And so what you see in these systems is recovery time measured in minutes if a server fails, small numbers of minutes, because you can do 1,000-way parallelism if you've got a big enough system. All right, let's take a break. Thank you very much.